Okay, so today we will continue to complete the proof of lemma 5.2.1. All right, so the statement is that for any non-negative random variable, capital X, its expectation exists. So, and this expectation can be written this integral. Okay, the integrand is the probability that random variable x greater than t, and so by using the CDF of the random variable x, all right, this probability is 1 minus the CDF of x at t. Okay. Okay. Now in step 1, so we have shown that the lemma holds for non-negative discrete random variables in step 1. All right, so now we'll proceed to step 2. X is an arbitrary non-negative random variable. Okay, so this is, and so we let x1, x2, be a monotone increasing sequence of discrete non-negative random variables which converges to random variable capital X. Okay? Then, by step 1, we have the expectation of xn is equal to the integration of over the semi-infinite from 0 to infinity of the probability that x sub n greater than t and dt. So this is here. Okay, for O(n), etc. Okay, so the expectation is here. Now, because that x1, x2, it is a multiple increasing sequence of discrete random variables. Okay. Since xn increase to x for any t greater than 0, we have greater than or equal to 0, we have that the event x1 greater than t is contained in the event x2 greater than t. Okay? Because if the value of x1 is greater than t, then the value of x2 at an outcome omega is greater than or equal to the value of x sub 1 at the same outcome omega and greater than t, so that this must be true. Okay. So we have an increasing sequence of events. Okay, so we have an increasing sequence of events. Okay. Now also, since x sub n is less than or equal to x, okay, so we know xn greater than t also contained in x greater than t. Okay, for O(n) greater than or equal to 1. Okay, and then that so the union n from 1 to infinity of xn greater than t must be contained in x greater than t. Okay. So first of all, we know that the union of this event, okay, is contained in this event. Now we want to show the converse inclusion. So, and for any omega in this event, okay, we have, of course, we have the value of random variable x at this outcome omega is greater than t. Okay. All right. So there must exist an n greater than or equal to 1, such that x sub n omega is greater than t, i.e. omega is contained in xn greater than t. Right. Otherwise, if not, so otherwise, the xn omega will be less than or equal to t for O(n) greater than or equal to 1. Okay? And then, right? And then the limit as n goes to infinity because we know xn is an increasing sequence of discrete random variables. So this limit exists and is less than equal to t. Okay, but we know this limit is equal to x of omega. Okay, since xn converge to x. Okay, so xn converge to x here. Right, so we have this one. But this is a contradiction. Okay, because we start with an outcome which is in this event, which means that the value of random variable x at outcome omega is greater than t. Okay, so that this is must true, right? So for every omega, all right? So that's omega in x greater than t implies that omega in xn greater than t for some n greater than 1. All right, and so this implies that omega is in the union of this event. Okay. Right, and which says that x greater than t is contained in the union of xn greater than t. Okay, so we have these two inclusion relationship. All right, so we prove that the union of x greater than t is equal to x greater than t. Or we can say that x greater than t is equal to the union of x and greater than t. Okay, and this is actually the limit. Okay, of this increasing sequence of events. All right, so this is the limit of xn and t. Okay, so we can apply continuity of the probability function. So by the continuity of probability function, the probability of x greater than t is equal to the limit, okay, of probability of xn greater than t as n goes to infinity. Right? So then by the definition of p of x with x non-negative, we have expectation of x, all right, is the limit and goes to infinity. Expectation of E xn here. Okay. Okay, first of all, Ex exists and equal to this limit, and this is limit. Okay. Okay, and all right, we here by step 1. Okay, we have this integral. Okay. Now we can exchange the order of limiting process and the integrating process, right? Right, and this is by the monotone convergence theorem. All right, and I will state this theorem later. All right, so the monotone convergence theorem guarantees that we can exchange the order of knitting process and the integration. Okay. And this limit, as we have shown here, is here. Okay, so we get the expectation A is equal to this one. Okay, so we have done. Yeah. So we have done here. Okay, so we prove the lemma for an arbitrary non-negative random variables. So let me state the monotone convergence theorem. All right, so let H1T, H2T, right? A monotone increasing sequence of non-negative functions. So you can see this is become bigger and bigger. Okay, so be monotone increasing sequence of non-negative integrable functions on an interval I in R. Okay, so it is integrable, which means that it's integral, okay, over the interval I is finite. Which converges to a function h of t, okay, for all t in I. Okay, so that is that. So let me say it the other way. Hn of t dt is finite for On, and the limit n goes to infinity hnt is equal to h of t for all t in R. Okay, so suppose we have such a monotone increasing sequence of non-negative and integrable function, okay, on an interval. And this monotone increasing sequence converges to h of t, okay, for all t in the defining interval. So, which means that this integral it always exists infinite, and the limit of h sub nt is equal to ht. Okay. All right. Then h of t is integrable over I. Okay, so h of t is integrable over I, and the limit of n goes to infinity of the integral of h sub n over I. The limit is equal to the integral of h of t over I. So which means that the integral of h of t over I can be obtained by taking the limit of the integral of h sub n over I. Okay, and so because h of t is the limit h of t, okay, so you see that, which means that the limiting process and the integration operator is exchangeable. Okay, so you can see you exchange the limiting process and the integration operator here. Okay, and to apply the monotone convergence theorem in here, so the h of n t is actually the probability that xn with t, and h of t is just the probability that x greater than t here. Okay? So the status is here, h sub nt is here, and h of t is the probability that capital X greater than t. Okay? And the function h sub nt is a monotone increasing function. It is because that we know that we have a monotone increasing sequence of events. So here we know that x1 greater than t is less than or equal to probability, x2 greater than t is less than, etc. Okay, and we know, so this probability is a monotone increasing sequence of non-negative numbers. So you can see here. Okay. Right. So this is bigger, this is smaller, and so the probability becomes increasing. All right. So here, so this means that increasing, right? So you have the increasing sequence of non-negative integrable function. And they are integrable. It's actually, we have shown before, okay? Because that we have shown that they are integrable. Oh, by the way, the interval I here, okay, is 0 to infinity. Okay. So we have, in step 1, we have shown that this is Hn of t, okay? So you can see that h of t, h1, this, and we know the approximation sequence of discrete non-negative random variable has finite expectation, okay? As we discussed the definition of the expectation of non-negative random variables. So that we know h of t in here, okay? So which means that okay. It's integrable over I. Okay. So we have a monotone increasing sequence of non-negative and the integrable function on an interval I which is equal to 0 to infinity. Okay. And the Hn converge to so in here, so we know this is h of t is equal to the limit of Hn of t. Okay, so we have so the sequence converges to ht. Okay, right. So the required condition, okay, has been satisfied by the previous discussion. Okay, so we all will use that. Okay, and so the conclusion is here. We can exchange the order of the limit. So this is h of t. Okay. All right, and we can exchange the order of integration and the limiting process. So this is h of t, and go to h of t here. Okay, so we have applied the monotone convergence theorem perfectly. Okay, just so what we have done here is actually a preparation to be able to apply monotone convergence theorem. Okay, so lemma 5.2.1 in the textbook has been proved rigorously. Okay. All right. So after we treat the expectation of non-negative random variables, we know it always exists and can be expressed in this way. And as I have remarked last Thursday, that because this expectation is equal to this integral. So you can see that this integral is independent of any approximation sequence of discrete random, non-negative random value over here. Okay? All right, so this result is independent of the selection of such an approximation sequence. Okay, so that's our previous definition of the expectation of a non-negative random variable is well defined. Okay. Okay, now we will treat a generic random variable. Now, for a generic random variable x, we define the positive part, we denote it as x sub plus, defined to be 0 if the value of capital X is negative, but will be the same of the value of random variable x if this value is greater than or equal to 0. Okay, so we define x plus to be this, and x minus omega. Okay, define minus x omega if x omega is negative, and 0 if x omega is non-negative. Okay. All right, so we define this for all omega in the sample space. Okay. And so we give them name, call that this is called the positive part of random variable x, and this is called the negative part. Of x. Okay, so we have positive part and negative part here. And as you can see, this is actually we saw all right, so this is actually a data processing of the function. So this is actually, you can see, it is the maxima of x omega and the 0. Okay, and this one is the maxima of minus omega and 0 here. Okay, so you can see this is so-called, this is G minus, okay, and what is G plus? G plus is that is the comparison of x and 0, so that this is you can say this is a rectifier. Okay, so So it is here. Okay. G plus of x. And the G minus is here. Okay. Okay. So this is another type of rectifier, right? And you can see that the both functions are continuous functions. Okay. Since G plus of x and G minus of x are continuous function, okay, on R, x plus and x minus, so the positive part and the negative part of x are non-negative random variables. So, because they are continuous, so x plus and x minus are random variables. But they are non-negative. Why? Because the value is always non-negative. Okay, as you can see, the rectifier. Okay, so the value of G plus and G minus is always non-negative. Okay, so you can see here. Okay, so we have the positive part and then the negative part, or they are non-negative random variables, and we know that x omega is equal to the x plus omega minus x minus omega. Okay. All right. So the original random variable is the difference of its positive part and its negative parts here. Okay. So we have that. All right. So now the expectation of a generic random variable x is defined as the expectation of its positive part minus the expectation of its negative part. Okay, so this is our definition. Provided us that at least one term on the right is finite. Okay, because we take the difference here, and we know that because x plus and x minus are non-negative, so their expectations always exist, but may be infinite. May be infinite. So if both of them are infinite, then you have infinity minus infinity, which is undefined. Okay, which is undefined. So we require that at least one of these two expectations is finite. Okay. Okay, so If both of them are finite, of course, the difference is finite. So we have finite expectation of x. But if the positive part has infinite expectation, and then the negative part has a finite expectation, then the difference is infinite. Okay. On the other hand, if the positive part has a finite expectation, but the negative part has infinite expectation, then the difference is minus infinity. Okay, so the expectation of a genetic random variable can be finite, our positive infinite, our negative infinite. Okay, in this definition here. Right. So a condition is that if both E of x plus and E of x minus are infinite, then x is said to have no expectation, which means that the expectation of x does not exist. Okay, so that is the. Okay, so up to this point, then we have defined the expectation of a generic random variable. Okay, in this way. Okay. Now, so we will derive a formula like lemma 5.2.1 for non-negative random variable, right? So we want to derive an expression of the expectation of a generic random variable. Okay, and then it is stated in proposition 5.2.h. Now for any random variable x, the expectation E of x exists, and this expectation can be expressed as a difference of two integral minus okay. Okay, so the first term is an integral of this integrand, this probability function, right? This probability for x greater than x over the semi-infinite interval from 0 to infinity. And the second term is another integral over minus infinity to 0. But here, the integrand is actually, you can see this is actually the CDF of capital X. Okay, so this is difference. And provided that, again, provided that at least one of the two terms on the right is finite. Okay, so at least one of these two terms is finite. Okay, if both of them are infinite, then the difference is meaningless. So in this case, so if both this and this one are infinite, then the expectation does not exist. Okay, so this is the okay. Now we give proof here. Right, since both x plus and x minus are non-negative random variables, so by lemma 5.2.1 we have that the expectation of x plus is equal to the integral of the probability of x plus greater than x dx. Okay, for x from 0 to infinity. Okay, but which means that the x, because x is always, the detail x is always non-negative. So the event here says that the positive part always positive. Okay, so when they're always positive, which means that x plus is equal to x. Okay, so this is the same. Okay, this is same that. All right. So the positive part, the expectation of the positive part is equal to the first term here. The first term. Now we see the expectation of the negative part. Now we know, again, by lemma 5.2.1, so this is x minus greater than x dx here. Okay, and again that when x is non-negative, so this event says that that the negative part always positive. When the negative part always positive, which means that here the value is equal to minus x. Okay, so this is equal to, will be a minus x greater than little x and dx here. Now we were, so this is probably x less than dx. Okay, so we multiply minus 1 on the both sides of the inequality. So we have this one. And when we do the change of variable, so we set x equal to minus y or minus t. Okay, so by change of variable, so this is becomes to 0 minus infinity probability of x less than t. Okay, and minus dt. Okay, and so finally we have minus infinity to 0 probability x less than t and dt. Okay, so we have this one. Now since since the PMF probability mass function, right, is positive for countable only for countably many x in R. So we have that if we integrate this PMF must be 0, okay, over the interval must be 0. Okay, so that this is 0, and then so that E of x is equal to so then by the definition of E of x, so this is equal to minus okay, so we include this. This is 0. All right, and minus okay. Okay. This, so that which exists provided that one of the two terms, okay, on the right is finite. Okay, so one of the two terms is finite. All right. So now we would like to merge these two integrals together, okay, when the expectation of x is finite. All right. So, but before that, we need a preliminary proposition. I if if this integral, oh, all right, so if this Riemann-Stieltjes integral is finite with the integrator a CDF, okay, with the integrator the CDF of a random variable, okay? Right, so if this is true, this Riemann-Stieltjes integral is finite, then the x of 1 minus f of x, okay, as x goes to infinity. Right, so we know this is actually as we know, this is actually the probability. Okay, maybe I will say a random variable x. Then this is actually the probability x greater than x. Okay, and as you see, when x goes to infinity, f of x goes to 1. Okay, by proposition 4.10. I think it's 2. Yeah. So this goes to 1, and so the difference is go to 0. Okay, so this term goes to 0. But the linear term goes to infinity. Okay. So we encounter a situation that we have, as x goes to infinity, this goes to infinity, this then goes to 0. So what is the limiting value of the product? What is the limiting value of product? And under this condition, we will show that, okay, the limiting value of this product is 0. Okay, and also, when x goes to minus infinity, this product okay, so and again, as x goes minus infinity, x goes to minus infinity, but f of x goes to 0. So we encounter a situation as this is tend to infinity, this tend to 0. And so what is the limiting value as x goes to minus infinity of this product? And again, this is equal to 0, okay, under this condition. Okay, so we see here. Now, since the Riemann-Stieltjes integral converges absolutely. Converges absolutely means because the integrand, we check the absolute value of the integrand. Okay, so over the whole real line, so that this is finite. So we have we have that if we integrals over this open interval, okay, maybe I use y for convenience. Okay. All right, so that this one as x goes to infinity. Okay, so this is upon x goes to infinity is that the Riemann-Stieltjes integrals here is actually equal to 0. Okay, and so this is the same as x goes to minus infinity when x is in and y is in minus infinity x. I use here. Okay. Because as we know that this is the limiting process. Okay. So as b goes to infinities, then it will converge to a finite value. Okay, and so this finite value is denoted as this improper Riemann-Stieltjes integral here. Okay, and so that so we can see the difference because that so let's see things. Maybe I will give the reason here. All right, and so because maybe I write here. All right, so since the limit all right, we know this is finite. All right, so the limit as b goes to infinity, the difference okay, so this is minus b and b y minus go to 0. Okay, so the difference goes to 0, and so that and the difference. Okay, so this is implies that the limit b goes to infinity. All right, and so the differences include the two branches, b to infinity, y, dfy, plus minus infinity to minus b, y, dfy. It's 0. Okay? So the difference is actually sum. And as you can see that each integral will be non-negative, so that when it goes to infinity, so that this b goes up, okay, just like x goes up, so this integral goes to 0, okay, and also as b goes to infinity, minus b goes to minus infinity, just like here. The x goes to minus infinity. Okay, so this integral, just like this integral, over goes to 0 too. Okay. Oh, okay. So that we know these two integrals has the limit 0. Okay. But for all x greater than 0, we have that 0 is less than or equal to x 1 minus f of x. Okay, so 0, because x always positive, and 1 minus f of x always always non-negative. All right, so the product is non-negative here. All right, and so this is x probability of x greater than x here. And then this is x and the y x to infinity. Okay, and d of fy. Okay, this is by proposition. So this is by proposition 5.1.c. Okay. All right. So this x is in an interval. Okay, and so we integrate the integrator, which is the CDF of x. So you get all right. Now, in here, that so you can move the x to. So this is equal to. Okay. So you had that. But for all y in here, by the way, sorry. For all y in this interval, y always greater than or equal to x. So we can have y here. Okay, so we have this, and we know this is equal to okay, because y always positive, okay, because x is positive, right? So we can replace y by its absolute value. Okay, so we have that. We have the bound. Now, as x goes to infinity, this integral here goes to 0. All right, so this, as x goes to infinity, this integral goes to 0, and the match with the lower bound. Okay, so this product will go to 0 by sandwich property, right? All right, so this is implies that so this implies that the limit x goes to infinity of x all right, so just conclude this is 0. Okay, things. Okay. Similarly, for all x is negative, so we have that the 0 is equal to minus, so minus x is positive, and the f of x here. All right, and so this is minus x probability, but x, capital X less than equal to x, and so this is minus x, and here is y in okay, again by proposition y.1 point C. Okay. All right, so that we can minus x here, minus x here. But you can see when y is in here, so that y always less than x, right, in this range. Then so if only minus y is going to equal to minus x. Okay, so that is upper bounded by minus y. Okay, all right, and so we can minus y, because y always negative, because x is negative, so this all the y in this interval is negative, right? So this is positive, and you get you can use the absolute value of y. Okay, so again, this product is bounded by 0 and this integral, but this integral goes to 0 as x goes to minus infinity. Okay, so this implies that as x goes to minus infinity, this product is equal to 0, since the limit x goes to minus infinity of y in minus infinity to x, y dfy is 0. Okay. All right, and so finally, x goes to minus infinity x times f of x is 0. Okay, so this concludes the proof here. Okay, so we have this preliminary proposition. Point to point J, all right, for any random variable x with CDF f sub xx, then the expectation E of x of capital X exists and is finite with the expectation equal to the Riemann-Stieltjes integral, okay, over the whole real line, provided that this Riemann-Stieltjes integral converges absolutely. I.e., this Riemann-Stieltjes integral, when we replaced the integrand by its absolute value, is finite. Okay. All right. So under this condition, that this random variable x has finite expectation, okay, and this finite expectation is expressed as the Riemann-Stieltjes integral here. Okay, so let's see the proof. Right, since we know this integral converges absolutely, okay, so we have that the limit x goes to infinity, x 1 minus f sub x is 0 and is equal to the x goes to minus infinity, x f of x. Okay, so we have this by proposition 5.2.I, which we just proved here. Now, also, since capital GY, okay, defined to be the y, the linear function, it's a monotone increasing function on 0 to b, okay, and this Riemann-Stieltjes integral is finite, implies that if with 0 to infinity, so if we just take a subinterval of the whole real line here, from 0 to infinity, okay, this Riemann-Stieltjes integral must be finite too. Okay, all right, but as we know, when y is in the range, so the absolute value of y is equal to y. So maybe so here we just write here. So this is finite. Okay, and so this is implies that from 0 to b, y dfy is finite. Right? So which means that, right, this is a gy, right? So as we know, this one is equal to gy. Okay, so which means that g is the Riemann-Stieltjes integral over 0b, right, with respect to f of x. Okay. All right, and so we know g is monotone increasing function on this finite cost interval from 0 to b, and g is also Riemann-Stieltjes integrable with respect to the CDF of x over 0 and b. Okay, and then we can apply the integration by parts for the Riemann-Stieltjes integral, okay, as stated in theorem 8, okay, in the notes, a brief of Riemann-Stieltjes integral, okay. So, okay, so this is for all b greater than 0. So we have that the CDF of random variable x is also Riemann-Stieltjes integrable over 0 and b with respect to g. Okay, and we know that the sum of the two Riemann-Stieltjes integral is equal to f of xb times gb minus f of x0 times g0, okay, by integration by parts. Okay, in theorem 8, in the note, a brief on Riemann-Stieltjes integral for all b greater than 0. Okay, so we have that. Now, since we know g of y is equal to y for all y in B. So we have, okay, so this is 0, so the product is 0. Okay, this is equal to B. Okay. So when we remove this term to the right hand side, so that 0 to B minus F, and this is dy. Okay, gy is y. Okay, so this is equal to 0b and y df. Okay, minus f of x minus b times f sub xb. Okay. Okay. So this one goes to here, give us minus sign, keep it here, and we move this goes to the left hand side here, becomes a minus sign. All right, and by adding b to both sides, so we have, when we add b there, this is 1 minus f of x, y, dy. And this is equal to plus b, 1 minus f sub xb. Okay? So when we add b here, okay, so we add b here. But b is equal to dy, right? So you can do that. You can the integral becomes 1 minus f of x of y. Okay, and then we take so that as b goes to infinity, so we know the improper integral is the limit for b goes to infinity for the integral from 0 to b, 1 minus f of x, y, dy. Okay, and do the substitution. So this is limit b goes to infinity, 0 to b, y df of x, y. Plus the limit b goes to infinity, b 1 minus f of x, b. But this limit go to 0. Okay, this limit go to 0. Okay. All right, and so this goes from 0 to infinity, y df xy. Okay, and you see here, this is finite, of course. Okay, because in here we know this is finite. This is finite here. Right. So this term can be replaced by. Okay, so this term can be replaced by this Riemann-Stieltjes integral. Okay, so this Riemann integral can be replaced by the Riemann-Stieltjes integral here. Okay, and we know it's finite, so this integral is finite here. right? And secondly, we want to deal with the second integral. Right, and similarly, since is finite, so this implies that if we integrate over the interval, subinterval from minus infinity to 0, also, okay, so this one is equal to minus y is finite. Okay, and because that in this interval, all y is non-positive, so the absolute value will be minus y. And so this implies that 0a minus y is finite. Okay, for all a which is negative. Okay, and so this implies that gy, so we name we define this as gy. Okay. All right, so this implies that G is in so that's just in A0 of f of x. Okay, so this g function, which is equal to minus y, is the Riemann-Stieltjes integral over this interval. Okay, with respect to the CDF of capital X. Yeah. Now, by the linearity of Riemann-Stieltjes integral, in theorem 4 in the notes, a brief on Riemann-Stieltjes integrals. So we have G defined to be minus G is in for OA. Okay. Okay. But gy, which is minus gy, is minus y is y. Okay, so gy is monotone, increasing A0. So we have again the CDF of x is also in this Riemann-Stieltjes integral over the interval from a to 0 of g. And again, so this is by the integration by parts. A to 0, f of xy, dg of y, plus a to 0, g of y, dfxy, equal to f of x 0, g 0 minus f of x a and ga. Okay. Okay. Again, by integration by parts. Okay. In theorem 8, in the notes on the Riemann-Stieltjes integral. So we have that. And this is 0, we know. And this is a here. Okay. All right, and so this is implies that a to 0, f of x, y, and the dy. Okay, because gy is equal to y. Okay, so this is equal to a to 0 minus y. Okay, and the df of x, y. So we just move this integral to the right hand side. Okay, so this is minus y, and the minus a f of xa for OA, which is negative. Okay. All right, and so we can take the limit. So the improper integral, okay, is equal to the limit a goes to minus infinity, 0 to a, and this is the limit a goes to minus infinity, a 0 minus y, df of xy, minus the limit a goes to minus infinity a times f of x a. But this limit is equal to 0, so that this is equal to 0 to minus infinity minus y, and d of fxy. And this is absolute value of y, and this is finite of 2 again. Okay, so this integral is equal to this integral, okay, and it's finite. So we conclude that expectation of x exists and is finite with, as we know, this is becomes 2 minus okay, and you combine together, you get okay, so if a generic random variable has finite expectation, okay, by assuming that this Riemann-Stieltjes integral converges absolutely, okay, then this finite expectation can be expressed by this Riemann-Stieltjes integrals. The integrand is just the linear function x, and the integrator is just a CDF of the random variable capital X. Okay. Now we consider a special case when random variable x is an absolute continuous random variable with a PDF f of x. Okay, so if this is the case, then the expectation of x exists and is finite with the expectation of x can be expressed as Riemann integral with integrand, which is x times the PDF of capital X, provided that the integral, the above integral here, converges absolutely, i.e., if we replace x by its absolute value, then this Riemann integral is finite. Okay. All right. So if this is true, then this absolute continuous random variable capital X has finite expectation, and this finite expectation can be evaluated by this Riemann integral. Okay. All right, and the proof is here. Since so this probability, because we have a PDF, okay, so the probability that random variable x is in an interval is that we do the integration of the PDF over the corresponding interval, I'm sorry. This is little x here. Okay. And will be that x, little x from okay. So we can express these two probabilities by Riemann integral here. All right? So we start with that. So now we have okay. So we look at this indigo. All right. So this is the iterative integral, right? Integration. So we integrate over y first and then x here. All right. So we'll look at the integration region here. For x is from 0 to infinity. Okay. So x is from 0 to infinity. And this is the line, y equal to x. Okay. For the inner integration, the integration interval is for y from x to infinity. So y for given x here, the integration is here. Okay. So you can see the region will be is here. So this is our integration region. Okay, this is our integration region. Now the integrand is very simple, right? The integrand is non-negative, right? The integrand is non-negative. So we can exchange the order of iterative integration. This is by Probability theorem. So we can do the right, but we have be careful. Now, y is the outer integration. So y is here. But we do the integration over x first. Okay, so for each y, the integration label is from 0 to y. For x is to y. Okay, so the x is from 0 to y. Okay, it's from 0 to y. Okay, so given the y, right, the x integrate, right, from 0 to y here. Okay, so this is y equal to x equal to y, the same. Okay, so once we change the order of integration, this is guaranteed by Probability theorem. Whenever the integrand is non-negative. Okay, and so now, what is this? Well, the integrand is independent of x. All right, so we can write here dx fxy dy. Okay, so the result of this inner integration should be a function of y. Okay, and it's actually is equal to y and fxy dy. Okay, so the first integral give us this Riemann integral here, and the second integral, 0 to minus infinity, the inner one, x from minus infinity to x, okay, and fy dy and dx here. Again, because the integrand is non-negative, okay, so this is non-negative. So by Fubini theorem, we can change the order of integration. Okay. dy here. Oh, by the way. Now, what is the integration interval? So we should look at the integration region here for this case. Now, here, for each y, for each x, right? X is from 0 to infinity. So x is from 0 to infinity, right? It's in here. And for each x, the y integrate from minus infinity to x. Okay, so we should have a line here. Okay, so that this line is y equal to x. Okay, so the integration would be here down to the minus infinity. Okay. So you know that the integration region will be here. Okay, this is our integration region. Okay. Now if we change the order of integration, so we fix a y. Okay, now this time we fix a y here. And what is the integration? It will be from x to 0. So this is from x to 0. Oh, oh, to y, sorry. To y. No. X is y. Y to 0, sorry. All right, so, so x is from y to 0. So x is from y to 0. Okay, and so once again the integrand is independent of x, so we can move to there, dx. So this is minus y and f of xy and dy. Okay, so the second equation is here. So together, right? And this is finite. Okay. This is also finite because that this is equal to this is finite. Okay? The reason is that this remains equal is finite, so that this implies that when we integrate over, it's finite, and we integrate over a subinterval, is also finite. Okay. So both finite. Okay, and so we conclude that. So we conclude that the expectation of x exists and is finite with expectation of x is equal to the difference of these two integrals, right? And so it's equal to 0 to infinity y f sub x y dy minus 0 to minus infinity minus y f of x y dy. Okay, so combined together, we get here as our result. Okay. All right, so now we prove proposition 5.2.1 in the textbook. Okay, but my statement is much more rigorous than the one given in the textbook. So let x be a random variable with CDF f of x and g a Borel measurable real valued function on R. Okay. Then the expectation E of g of x, all right, because g is Borel measurable on R, so g of x. So when we do the data processing on random variable x by g, the result g of x is again a random variable. Okay, and its expectation of this new random variable exists and is finite with this expression right, expressed by this Riemann-Stieltjes integral with integrand, this Borel measurable function g of x, and the integrator is the CDF of the random variable x. Okay, provided that this Riemann-Stieltjes integral converges absolutely, i.e., if we replace the integrand by the absolute value of the integrand here, then this Riemann-Stieltjes integral must be finite. Okay, this is the first part. And if x is absolutely continuous with a PDF f of x, then the expectation of g of x exists and is finite with this expression as a Riemann integral, but the integrand is the parametric function g of x times the PDF of x. Okay, provided that the integral converges absolutely, i.e., this integral is finite. Okay, now I give a proof. From proposition 5.2.h, I think time is so limited. Okay, maybe I'll give you the proof. Please see a note. The proof of this proposition. Okay, so I'll give you a proof of this proposition, and the idea has been covered in the proof of previous propositions. Okay. So I have some time, so I'll give some new definitions. The nth moment. So we define the nth moment of discrete random variables, and now we are able to define the nth moment of a generic random variable. Okay, it's the expectation of the nth power of x. Right, so that this is, so the parametric function is the power function. Okay. Right, provided, of course, provided that this Riemann-Stieltjes integral converges absolutely. Okay, so if this Riemann-Stieltjes integral converges absolutely, then the nth moment is well defined and is finite, of course. Now assume that x is a random variable with a finite mean. We call eta, and we know finite mean is just the expectation. Now, the nth central moment of x is defined as the expectation of x minus eta raised to the nth power. Okay, and so can be expressed by the Riemann-Stieltjes integral here, like here. Okay, provided that this Riemann-Stieltjes integral converges absolutely. Okay, so we know that this is actually the application of and here the application of the previous proposition. Okay, in here. Okay, so we just use a appropriate Fourier measurable functions here. Okay. The second central moment of a random variable x is called the variance over dispersion of x, denoted as VAR x. Okay. And the square root of the variance of x is called the standard deviation. The standard deviation denoted by SD of x. Okay. Right, so it's and variance plays an important role in probability theory as well as in statistics. Okay, so I would like to write down a proposition for variance. So a random variable x has second moment ES square if and only if x has finite mean and finite mean eta and finite variance VAR X. Okay. And in this case, so we have the relationship that the second moment is equal to the variance of X plus the square of the mean. Okay, the square of the mean there. Okay, and so again, please see where I will give you a note. Please see a note on this proof. Okay, so right, so we complete the second section of chapter 5 for sections 5.3 to 5.6. Please read. The textbook. Okay. So in these 4 sections that the textbook introduced several important PDFs, okay, for various absolute continuous random variables, including the uniform disputed PDF, which we have introduced before, and the normal probability density function, which is quite important, and exponential PDF, and as well as gamma PDFs. Okay, so they are important probability density functions as models for absolute continuous random variables. Okay, so you have to study the material in the textbook so that you are able to solve the recommended exercise problems. Okay, and so next Tuesday I will discuss functions, how to find a PDF of a function of an absolute continuous random variable. Okay, so, all right. So now I stop here.